Okay, now let's say that I get a certificate and I'm looking at it. I want to make sure that it's valid. And there's a bunch of checks that I'm going to do. I'm not going to give you a complete list of all the checks, but I'll give you some of the major ones. And the reason I'm giving you these ones in particular is because I have a story for more or less each of them. Okay, so the first thing that we all know is when you get a certificate, now we all know it, we look at it and we see that it traces back to a root certificate. So the certificate was signed by a CA, and that CA was signed by another CA, and eventually we find a CA that signed everything that is in our computer already. It's already hard-coded in our computer. Another simple thing is if Concordia.ca is saying, hi, I'm Concordia.ca, here's my certificate, that certificate better be for Concordia.ca, right? If you go to Google, like say I have a certificate for my domain, which is pulpspy.com, and I'm in the middle of your connection between you and Google, and you say, hi, Google, I want to talk HTTPS, and Google says, great, here's my certificate. I just replace that with my certificate for pulpspy.com, right? Will you then start sending traffic to Google that's encrypted for the key in my domain? The answer is no, because my domain is different than the domain that you're trying to connect to. You know you're trying to connect to google.com. You're getting a certificate for a completely different domain. That certificate doesn't mean anything as far as that connection is concerned. Okay, so it's a simple thing, but you got to check it. We mentioned that what happens if, again, let's say I actually have a domain, say I pulpspy.com. What happens if I go and start issuing certificates for, say, google.com and facebook.com that chain back to this certificate, right? So I have this certificate. It does chain back to a root certificate. So why can't I issue certificates? And now I'm just part of the chain. Okay. And so the answer is that whenever a CA gives you a certificate, there's a flag that says you're not a CA. It says CA equals false. And when the CAs have their own certificates, they have this flag set to true. Okay. And so you can see this. It's called basic constraints. It's one of the things that's in all those details about certificates. So you can see Concordia certificate. It's not a certificate authority, which means it can't issue further certificates down the chain. It can try, it can do it, but your browser should reject it because when it starts chaining back, it will eventually hit this certificate. It will say, hey, this certificate's in the middle of the chain. Therefore, it's a CA. It's acting like a CA. But when I go look at the certificate, I realize that the flag for it to be a CA is set to no. Okay. And again, Concordia can't flip that flag. What if I just write yes in there? Well, it breaks the signature. So Global Sign signed off on this certificate. And so when Global Sign signed off on this certificate, they made sure, or they were the ones that wrote in no for certificate authority. So Global Sign's only going to sign off on non-CA certificates and give them out as site certificates. Okay. Now, if I go up one in the chain to Global Sign, then I see that the CA flag is tagged as yes. Okay. There's certificates don't last forever. I think I mentioned this in passing. Usually they have a shelf life about 1 year or 2 years now. It used to be longer. And there's also what happens if you lose your key. Let's say you wake up and you realize that someone broke into your server and they stole your key, and now they could be out there impersonating you. Can you do something about that? And so the answer is yes. You can try and revoke that certificate or advertise the fact that that's no longer a valid key for you. And we'll think about a bit about how you do that and whether it works very well or not. It turns out it doesn't work out very well. Okay, so let me do some stories that connect to these issues. Okay, so this is an older story. It goes back to 2014. This is an implementation issue. Again, it was a pretty famous one when it happened. It was a problem with Apple's library for SSL. So Apple's library is called Secure Transport. That's the version number there is the one that was vulnerable, plus earlier versions, I'm sure. And the whole thing is called go-to fail. Okay, so this is like really, really loose code, pseudocode, high level, but it will give you the sort of the concept of what's happening. Okay, so we have some code, and what this code is doing is it's checking those conditions on a certificate. So I mentioned there's all these things that you have to check. There's lots more, by the way. This is just some highlights of things that you need to check, and that's what this code is doing. So it's basically saying, okay, I'm going to check condition 1, and if it fails, then I don't need to check condition 2, 3, or 4. I can just quit early because once it fails, it's going to fail. So I'll go down and I'll fail. Otherwise, I'll keep going. I'll check condition 2. I'll check condition 3 and 4. Okay. Now, the code was written in a slightly weird way. So what happened is they had a variable called check, and it held an integer or a Boolean. So either 0 or 1. 0 means everything's going well, and 1 means that it's an error. So it's like a flag for an error. Okay, so what they would do is they would check condition 1, and they would write whether it passed or failed into this variable. And if the check was flagged for an error, then what they would do is they would go to fail, which means you skip all these lines of code and you go down to the bottom, and then the bottom would just return this variable check. So whatever code was calling this would get back a 1, and a 1 means there was an error. Okay. Now, if the condition passed, it would write a 0 in. Because check is not equal to 1, it's equal to 0, meaning it's passing. We skip this line, go to fail, and then we go to the next line of code, which is going to check condition 2. Same thing. So it writes whether it passed or failed into check. We check whether it failed. If it failed, we go to fail, and if it didn't fail, we skip the go to fail, and we go to the next, checking the next condition, onward and all the way through the code. Okay, so this is roughly the structure of how the code worked. Okay, now the code that's on the slide is fine. There's no problem with the code that's on the slide, and the code on the slide is not the code that was in Apple. Okay, this code that was in Secure Transport was very, very similar, but it just had one line difference, which is that in one of these conditions it had an extra go to fail. Okay, so that's it. So it looked like someone maybe made a copy and paste error. They were copy and pasting a bunch of stuff, and they accidentally put in an extra go to fail. Or it looks like someone was being very, very clever, and they knew that this is the kind of thing that wouldn't, raise alarms, but is actually a very devastating thing to do. Okay, so let's think about what this extra go to fail does. So let's assume that condition 1 passes. So check is not equal to fail or error. So we're going to skip go to fail. We're going to check condition 2. Okay. Now let's say that condition 2 also passes. So we write pass into check. Check is not equal to 1. So what we do is we skip something. Okay. The idea is that we're going to skip and go down to the checking condition 3. Okay. But what does this extra go to fail happen? What happens? What's the extra, what's different about this code now that we have a second one? Okay. So when check is not equal to 1, okay, so it's not equal to an error, we're going to skip the if condition. Okay. So we're going to skip the if condition. The question is the if condition go to fail the first one, or is it both of them? So are both of these under the if, or is it just the first one? And the answer may have to do with the programming language. So some programming languages might say, well, it looks like both of these are a condition because they're both indented. And other programming languages will say, if there were curly brackets here, right, and the curly brackets included both of these lines of code, then we would consider them together. But if there's no bracket here, then we just assume, strictly speaking, the next line is what is under the if, okay? And anything that comes after that is where we skip. So we just skip the next line, and then we go on to the line after that. All right, and so the programming language that this was written in, Objective-C, I think, I'm just guessing because that's what Apple uses, was such that that the thing under the if condition was just the go to fail, the first one. Okay, so the fact that there was a second one here means that this is the next line of code that you execute. Okay, so let's take this from top to bottom with that in mind. Condition 1 passes. Check is not equal to 1. It's not equal to an error. So I skip go to fail. I go to check 2. Check 2 passes. Check contains 0 because it passed. Check is not equal to 1. It's equal to 0 because it passed. It's not equal to an error. So I skip the next line of code. The next line of code says go to fail. So I go to fail. And when I go to fail here, I return. Notice I don't return, oh, it failed. You know, even though like I should only hit go to fail. But what I return is the value in check. What's the value in check? Well, it passed condition 1 and it passed condition 2. So there's still a 0 in this variable check. And so it's going to return a 0, meaning that the whole thing passed. Okay. Now, the key point is that because of the second go to fail, I can never reach these lines of code. Okay. It doesn't matter. I fail here. If I fail in condition 1, you know, then I go straight to fail. If I fail condition 2, I'm going down to fail from this first go to fail. And if I pass conditions 1 and I pass conditions 2, then I go to fail because of the second go to fail. I'll never check condition 3 and I'll never check condition 4. Okay. But what if condition 3 and 4 are really important? What if they include things like, hey, you just gave me a certificate. I see the certificate is pulpspy.com and I'm going to facebook.com, right? Is this a valid certificate for that website? That's the kind of thing that could be in condition 3 and was indeed in condition 3 or 4, one of the conditions that was unreachable in this particular library. Okay, so what was happening because of this extra go to fail is it was skipping some critical checks. And one of those checks was just, does the certificate that's being presented even match the domain that I'm trying to visit? And because that was skipped, if everything else about the certificate was valid, what you could do is you could use any old certificate that you had that was still not expired and was actually issued by CA, et cetera, and you could use it to impersonate any website on the web, assuming that the user was connecting using Apple's secure transport. Okay, so this was bad news. Some people said, okay, how can we prevent this in the future? So you can always write better code, obviously. And then what was interesting to me is lots and lots of people came out of the woodwork and they said, oh, we have these tools, these automated static analysis tools, and you put your source code in. And Apple's source code isn't always open source. Not their whole operating system isn't open source, but some of the components of their operating system are open source, and this was one. So you could actually get the source code for this. And so people are like, we took their source code, we ran it through our static analysis tool, and our static analysis tool flagged it. It said there was a problem here. What's going on at Apple? What's wrong with Apple? Why aren't they, using tools like this? Otherwise, they wouldn't have made this embarrassing mistake. Okay. And that tells half of the story. So I don't doubt that their tools were flagging it. The problem with these static analysis tools is that they also flag lots and lots of stuff that are not errors. So you get a whole bunch of flags on a whole bunch of stuff, and then it's like you need an engineer anyways to go through and try and figure out which one's a real one and which one's some sort of false positive. Especially this in terms of the state of the art in 2013 or whenever this happened. Okay, so Apple probably was using static analysis. It was just it returned so many false positives that they missed the fact that this was not actually a true or a false positive. A better approach is to do unit testing. So unit testing would be you have a bunch of certificates and they're bad, and you just run them against your library and you see whether it rejects them or not. And so somewhere in your pile of bad certificates that should never be accepted would be a certificate that was for a domain that's different than the domain that you're trying to visit. If you run that certificate through the library and it fails, then there's an error. You don't necessarily know what line of code is causing that error, but that there's something wrong with that library, and then you're going to go digging and try and find out what it is. Okay, so that's a much better approach. And what researchers did around that time is they said, oh, that's such a good approach. Why don't we actually do that? Why don't we go grab a bunch of SSL libraries and we'll come up with all sorts of weird bad certificates, and we'll just try them and see if we can find other cases of bad certificates that are accepted by these libraries. And what we can do is we can make the certificates really, really weird. Like we can put code in instead of data for fields, or we can do random things, or we can have certificates that just sort of end early, or we can take a bunch of certificates and kind of blend them together, like take a piece of this certificate and blend it with a piece of this certificate. Like computers can generate this stuff so fast, we can try all sorts of weird combinations. We can try 1 million combinations a second. We can maybe find some interesting things. So that general approach is called fuzzing, where you take something that's valid, but then you fuzz it. So you make a bunch of invalid variants of it. And then you just unit test the code. And if you find something that works, that passes when it shouldn't, then you can dig into the details and figure out why. And then usually you can write like a clearer rule. It's not just like, here's some weird certificate that passes and we don't know why. You reverse engineer out why, and then you also can fix it as a result. Okay, so there were a bunch of papers on kind of like fuzzing, or the idea of combining different certificates was called Frankencerts, and running them against libraries. And these researchers found lots of vulnerabilities, and we're all the beneficiaries of that research because the libraries got fixed. And so now they're pretty robust even against weird certificates. Okay, another thing I mentioned, I think twice now, is what if you have a site certificate, a valid certificate, and you just pretend that you're a CA even though you're not, and you just start issuing certificates. So I have a certificate for pulpspy.com, and I just start creating Google certificates, and I sign it with the key that's in my pulpspy.com certificate. And then my pulpspy.com certificate chains back to Let's Encrypt, and Let's Encrypt's a root in, or it has access to a root that's in your computer, right? Why wouldn't you accept that as a valid Google certificate? It traces all the way back. And the answer is that one of the links in the chain, which is my certificate, is not a CA. So I wasn't allowed to issue certificates. I was allowed to be the last certificate in a chain, but I wasn't allowed to be a middle certificate in the chain. Okay, so we need to check that that's true, that all the middle certificates in a chain have the CA equals true field set. And would you believe it? Some libraries didn't actually do that check, even though it was really basic. Okay, so one was Microsoft Internet Explorer in 2002. It was discovered that they didn't do that basic check. Okay, now everyone said, "Oh, that was dumb, bad implementation error." Now we know that. Well, no one's ever going to do that again. Okay, then Apple came out with a brand new invention called an iPhone, and for whatever reason, Apple decided that, hey, instead of using this, operating system that's been running on MacBooks forever, and maybe scaling it down for our phones, we're going to rewrite a complete operating system again. Okay, we're going to write an operating system from scratch called iOS. And that means we're going to redo all the SSL. We're going to redo the browser, everything. Okay, and so they have this brand new library. Guess what they forgot to check, right? They forgot to check whether certificates, all the certificates in the middle of a chain were actually CAs or not. And then everyone said, okay, that's dumb. Fool me once, fool me twice. Then we have all these IoT devices that start coming out like around 2000, COVID times. And again, they're rewriting operating systems, right? They can't run full scale anything, maybe a scaled down version of Linux or something. But, they're for a lot of times they're either doing a custom operating system, or they have some scaled down version of Linux that doesn't have an SSL library. And so they're writing the SSL library for that scaled down version. And they're doing it from scratch. And again, they're not checking this field. Okay. But the good news is, of course, it's not going to happen again, right? Okay. Another thing you could do is you could just do it anyways. So what happens? Okay. Let's say that this vulnerability doesn't exist, and you just start issuing certificates that you shouldn't issue. Let's say you're not even a CA. I'm not a CA, but I'm just going to create certificates. When I see people trying to connect to Facebook, I'm going to drop my certificate in, and that's it. It won't chain back to the trusted root store, right? So what's the browser going to do? Are they going to close the connection? Are they going to reject it? Like, what exactly happens? And so the answer for a long time, by the way, this happened, there's a real life example. But the answer is that actually what the browser would do is it would say, you know what, we're not like confident enough to reject it. We actually want you, the user, to decide what you want to do. Maybe there's some reason why you want to go to a website that doesn't have a valid certificate. Okay. And at the time, there were people who didn't believe in paying money to CAs to have their certificates signed. So they would run websites and they would just have self-signed certificates that didn't chain back to anything. Okay. So browsers said, well, we'll just let the user decide. And so they would show them a warning that looks something like this. Okay. So there's a problem with this website certificate. You know, do you want to click on the green thing and go to the website you're trying to go? Like, you know, imagine someone that doesn't know anything about security. They barely know how to use a computer. They just want to check Facebook, right? And they see this. They have no idea what it means. And they know if I click the green thing, I can go to Facebook. And if I click the red thing, I can't. What do you think they're going to do, right? Well, you don't have to guess. There were some studies, usability studies, and they found that lots of people are not going to click the red thing. Most people are just going to click the green thing. Okay, they're just going to go to the website anyways. All right. And so then researchers, particularly at Chrome, they sort of led the charge on this. Is they said, okay, well, what's going wrong here? So they said there's probably two things that are going wrong. The first thing is no one can understand what this means, right? It's actually not that confusing, but I've seen worse ones where like it's just a bunch of technical jargon and you can't really understand, you know, like I don't know what a certificate is or a certificate authority or anything like that. Okay, so if we're going to do this, we need the user to really understand what they're doing. So when they're clicking here, they understand what they're clicking on. And secondly, we shouldn't make it quite so easy to click, right? It's very easy to just click the green thing. In fact, the fact that it's green as opposed to red, it almost, you know, makes you want to click on it without even reading it. All right. So what Chrome did is they proposed, okay, let's fix the language. So first off, the language is a lot better. Your connection is not private, period. Okay, X, no bar. Okay. Attackers might be stealing your information. For example, passwords, messages, and credit cards. Okay. So this doesn't say anything. The word certificate isn't in this anywhere. The word certificate authority isn't in this anywhere. There's no talks about keys or anything like that. Doesn't mention SSL or TLS or HTTPS, none of that stuff, right? So it's very straightforward. It's easy to understand. And you have a big bar that says back to safety, and there's no option to just continue onto the website otherwise, unless if you clicked on advanced. If you click on advanced, then the second thing appears. Okay. And now it gives a little more technical detail because this is advanced. Okay. So it notes that maybe it's a misconfiguration. So we are acknowledging that maybe you want to go to the website anyways, but it could also be an attacker intercepting your connection. And if you really want to go to the website, now you can click on this. It will take you to the website, but it's very clear that it's marked unsafe. Okay, so this warning, the change from this to this, didn't take anything away from the user in terms of their freedom or their right to go to websites that have invalid certificates. But what it did is it really tried to clear it up. Okay. Then they did a bunch of user studies and they proved that users do the right thing more often when they see a message like this. So warning screens have improved since 2011. 2011 being this one, not this one. Again, I mentioned this website again. badssl.com, so you can try it yourself. So if you want to go to something that, for example, is self-signed, or let's put untrusted root. This is what Safari says today. So it says this website may be impersonating this website to steal your personal or financial information. You should close this page. This connection is not private. So you can see the language is almost the same as what Chrome tested, just slight variations. And I can close page or I can show details. So I have no option of continuing to the website from this. If I want to continue, I have to first click show details. Then it gives me a bit more technical information. Then it asks if I want to look at the certificate. And then it says, if you understand the risk involved, you can visit this website anyways. And then if I click on it, there's yet another warning. and it just says, are you sure you want to visit this website on a connection that is not private? Okay, so very clear this isn't a private connection anymore. Then if I click through, eventually I can get here. And now I'm on this. Now, interestingly, it's not saying not secure up here. Okay, so because I approved it basically and said that, I'm fine with this certificate, it's now saying, okay, you do have a secure tunnel to this website. It's just based on the fact that you click through a bunch of warnings in order to get there. Okay, and then the website has other variations on other things that can go wrong. You can look at it at your leisure. Okay, here's another kind of thing that could go wrong. So this is sort of a weird attack, but I thought it was okay. It's called a parsing error. So let me just go through the details itself. Okay. So what happens is you go to a CA and you say, I want a certificate for a certain domain. I want it for pulpspy.com. And the CA is going to say, okay, we're going to send an email to admin@pulpspy.com. Okay. Now, what if you go to the CA and say, I want a domain name, and here's the domain name. The domain name is, I want a certificate for a domain, google.com null character.concordia.ca. Okay. Now, the CA, when it looks at this domain, again, this is automated. So this isn't, a human's not looking at it saying that's weird, right? This is computer code. It's just parsing this string. And parsing is like kind of difficult. Okay, there's lots of different rules, and we know that like different code might parse strings differently in special cases. Lots of strings that you see are pretty well structured, but this one's a little bit weird. So how am I going to parse this string? What am I going to do? Okay, so there's basically, the way I see it, there's maybe more, but there's three basic things that my code would do. Okay, the first thing it would do is it would say, I see a character in there that I don't recognize. It's not a proper Unicode character. And so I'm just going to reject it. Let's just stop this process at this point. Come back to me later if you have a proper string. Okay. So that would be great. That's what code should do. Okay. However, some CA's code did not do that. Okay. So some CA code tried to process it anyways. The second thing is it might look at this and say, I don't recognize that character. It's an invalid character, so I'm just going to drop it from the string. Okay, so if I drop it, then what I think you're asking about is google.com.concordia.ca. Okay, is that a valid URL? It's kind of a weird URL, but there's nothing invalid about it, right? It's owned by concordia.ca. Com is a subdomain of Concordia, and Google is a subdomain of com. So it's google.com.concordia.ca. It's not that much different than users.encs.concordia.ca, which is where a bunch of websites are for professors. So it's just a subdomain of a subdomain of a domain. Okay. And the person that controls that is concordia.ca. All right. Now there's a third option. If you've looked at programming languages that are very lightweight, things like C. So a lot of programming languages, say Java, if there's a string and they write it to memory, they're going to say that it's a string, and they might have the length of the string and things like that. So they don't just write the raw bits of the string. They also like encapsulate it in the concept that it is a string, and they put that into memory. And so when you pull it back from memory, you're very clear about what you're getting and how long it is and things like that. Okay, C doesn't work that way. What C does is it just says, you want to write a string to memory? Great. Give me the first location in memory where you want me to start writing the string, and I'll write it there. Okay. Then later, when you go back to read the string, same thing. You just get the memory location, you jump to memory, and you just start reading the string. Now, the problem is, how do you know when to stop? Because memory's full of a bunch of things, right? There's not just your string there. And so what C says is, well, we don't know how to stop. And so this is what we're going to do. We could have the length, but then we'd have to encode it, and then strings are going to take up more memory because we have the length of the string. So we're just going to have this convention that if you want to end a string, you write a null character as the next character, and then that's considered the end of the string. Okay, so we call it a null terminated string. So it's something that some programming languages use. Okay, if you were to look at this and your code was using that convention of null terminated strings, it would think you're asking about google.com, because it would hit the null character and then it would just stop reading the string. Okay, all right. So here's the three options. We could just reject it. We could drop the null character, in which case we think it's google.com.concordia.ca, which is a subdomain of concordia.ca. Or we could read until we hit the null character. Then we could terminate the string. Then we think the person's asking for a certificate for google.com. Okay. Now, the problem here isn't which of the three that you choose to do. Okay. So it doesn't really matter. You can do one, you can do two, you can do three. They're all sort of valid approaches. One is probably the safest, right? But these two are fine in and of themselves. There's no attack if everyone does two and if everyone does three. Okay? But notice I said if everyone does. The problems arise when some people do one or two or three and some other people do a different one. Okay? So in particular, let's consider one scenario. Let's consider the scenario that the CA is doing number two. They're dropping the null character. And the browser, when the browser receives the certificate when they're trying to connect to the website, they see the same string in the certificate. And when the browser sees it, it's programmed, say, in C, and so it thinks it's a null character, so it terminates here. Okay, so what that means is I go to the CA and I say, I want a certificate for this. And it says, okay, you can have it if you're concordia.ca. Let's say I am concordia.ca. So now I have this certificate, this weird certificate on this weird string, right? But I was able to get it because I was able to prove I was concordia.ca because the CA was dropping that null character. But then I see someone going to google.com and I want to intercept their traffic. I drop in this certificate with this weird string, and it gets sent to the user's browser. And the user's browser is different. It's going to parse it as three. It's going to consider it null terminated. And it's going to say, okay, I see a certificate. This is a certificate for google.com. Okay. And so then it's going to accept that as google.com. Okay. And so concordia.ca, you can replace, the adversary can replace it with their own domain. And the thing that they put out in front can be all the common domains that they might want to intercept traffic to. Okay, so this effectively is, you can use it like a Google certificate, even though it's a Concordia certificate, depending on how people parse it, kind of thing. Okay. Okay, the next topic I want to talk about is revocation. So let's say that you are Concordia or a server. You lose the key, the long-term key that's in your certificate. Now anybody that has that key can impersonate you. Okay, so they can basically essentially read the connection, all the information that's in the middle. So what do you do in that case? So you might say, okay, well, I'll just make a new one, right? I'll stop using this old certificate. It's compromised. I get a new one. Okay. Does that solve the problem? Well, from your perspective, it does. But in terms of the adversary's perspective, what they can do is, let's say Alice connects to you, you send your new certificate. What they can do is they can just drop in the old certificate, right? And then you'll end up using the old certificate yourself because you don't know the difference. You don't know that there's a new certificate, okay? So as long as that old certificate is still valid, then you can still use it as an adversary in the middle in order to in order to do a man-in-the-middle attack. Okay, so it's not enough to just get a new certificate. You also have to cancel the old one somehow. Okay, so that's what we call revocation. So revocation is the term for canceling the old certificate. Okay, so how are we going to do this? How are we going to revoke a certificate that's already out there in circulation? Okay, and notice the only way we can really revoke it is Alice has to know that it's revoked. Okay, so somehow Alice has to learn that information. If she doesn't learn that information, right, then she'll never know that it's been revoked. So there's essentially two options, and neither of them are that great. I should say actually there's probably more than two options, but there's two options that are used in practice. Okay. So the first one is called a status check. Okay. And this is the idea. So the idea is that when Alice connects and gets the certificate, she's holding the certificate now in her hand. Before she fully trusts it, she does all the checks on it. It's valid, it's signed, it traces back to the root authority or whatever. So there's nothing wrong with the certificate itself. But before she says, okay, I'm finally done checking this, she does one final check. The final check is she'll ask someone, is this certificate still valid? I see that it was valid for sure, right? But as of right now, as of this second, is the certificate still valid? Okay, so she'll send that message, and then she'll receive a response that will be yes or no. Okay, so the protocol for doing this is called OCSP, Online Certificate Status Protocol, and the server that you ask for, or that you go and ask whether it's revoked or not, is specified in the certificate itself. So the certificate, in one of those fields, remember there's a whole bunch of fields in a certificate, one of those fields will have the OCSP responder, which is the server that you can access. Okay, so what you'll do is you'll basically just send, say, a fingerprint, like a hash of the certificate, to this URL. And then this URL, this would be for a Concordia certificate, then this URL will respond yes or no. This is hosted by GlobalSign. GlobalSign is the CA that issued the certificate. And so that's what is standard, is that the CA that issues the certificate are the ones that are going to put this up. Okay, so CA's job doesn't start and finish when they issue the certificate. They also are expected to stay online and run a server so that they can field all of these requests about whether the certificate's been revoked or not. And then if there is a revocation, and the CA, first off, the revocation doesn't take hold until the CA that issued the certificate realizes it. And once they realize it, then they can change the responses and start saying, yeah, this actually has been revoked. So let's say that, you look at this whole CA business and you're like, wow, there's a lot of money to be made, issuing certificates. And I don't have to do that much work. I just have to send some emails to admin@domain.ca. And then I have this server there that's running, that's responding. Okay. And so you're like, I'll do it for almost free. And you undercut the market. Now, technically today you can get free certificates, so you can't undercut the market anymore. But just for the sake of a story, now Google, Facebook, Twitter, well, X now, they all come to you and say, great, we want you to be our CA. Okay. And so you're really, really happy. Okay. But what happens? Okay. What happens is every single time someone goes to google.com, they do it securely. They get a certificate for google.com. Now they're coming to you and they're saying, has this certificate been revoked or not? So for every visitor to Google, which could be, I don't know, tens of millions a second. I don't know exactly how many they get. They get a lot, right? All of that traffic is now also coming to you, or at least one packet of it is coming to you, asking you about these certificates, okay? Plus all the traffic to Facebook, all the traffic to Twitter, all right? So you're going to have a pretty robust service in order to answer all of these requests. And it would be very easy, if you weren't prepared, to get overwhelmed by all of this traffic, okay? And so these OCSP responders getting overwhelmed by traffic became just the standard story of the internet. So what would happen is you would connect over HTTPS, you get the certificate, you would try the response, but most of the time, every now and then you would actually get a response, but most of the time you just wouldn't hear back. Okay? So what do? Let's say you're a browser. What do? So you have two options. You could say, well, we're going to throw an error or a warning or something like that if we don't get a response back. Okay. But the problem is that this is happening 90%, 99% of the time users go to any website. And remember that just because you go to one website, it's usually weaving content in from lots of different websites. And so you're doing these certificate checks for all of the resources that are loading on the page, not necessarily just the root page. Okay. And so basically you'd be seeing an error every time, right? Basically every page that you go to, you'd be getting one of these errors. And so browsers said, we can't have that. Okay. And so what we're going to do is we're going to fail open, right? So I remember I mentioned this a few times. We have this distinction between failing open and failing closed. This is another example of a fail open or an opportunistic protocol where you do the revocation check anyways. You just try and do it. But if you don't hear back, then you assume everything is good as opposed to assuming everything is bad. Okay, so you do your best effort. You don't hear back. Then that's it. Okay, so what can the attacker do? Let's say that they have a certificate. It is revoked, right? And the user is checking whether it's valid or not. Okay, and the responder is online and it is responding and it's saying, no, that's not a valid certificate. What you can do is simply drop that packet. Just never let it reach the adversary. Reach Alice. Alice will sit there. She'll wait for it, for a millisecond or whatever. And then her browser will say, well, I guess I'm not hearing back, so let's just assume it's okay. All right. So this revocation, because it fails open, it basically doesn't solve anything. It doesn't protect against someone that's in the middle because the person in the middle can also drop the response that you get back. Okay. And so this was the status of OCSP for a long time. Okay. Recently, as of 2026 is when I'm making the slides, but sorry, these guidelines were older than 2026. They were introduced earlier. But as of today, when I'm recording this, there are guidelines for EV certificates. So remember, EV certificates are the certificates where you check everything about the company and you check that they're that they're a registered business and you get their registration and you put that into the certificate and things like that. Okay. So they're like the sort of high integrity certificates that are offered. And so, there's a sort of agreement. So these guidelines they're guidelines. They're not like laws or regulations. They're not from governments. They're just from a consortium of all the CAs and the browsers, or a lot of them, called the CAB form. So they're not binding. But anyways, there's basically this agreement that if you're going to issue one of these EV certificates and you want to stay on the browser's good side, then what you need to do is you need to make sure that now you do have OCSP responders that are going to be live. Okay. And so the browsers don't really check this for OV or DV certificates. I'm also not sure to what extent they check it, but there seems to be some level of oversight over this for it. Okay. So today, what happens if we have the story that's on the slide? Okay. And Alice sends a request, and now it's one of these ones that that has to respond. It's an EV certificate. Okay, so because it has to respond, it may be the case. I'm not sure if browsers have turned it on, where now they're going to fail closed if they don't receive a response. Okay, so this seems to solve the problem. If we just enforce OCSPs to be live and we fail closed, then there's nothing the adversary can't do, right? But it turns out there's still a little bit that the adversary can do. So there's two things. The first thing is that what the adversary can do is they can get an OCSP response on the certificate that they're about to attack. So they attack a certificate, they steal a key. Alice doesn't realize it yet. Okay, if she never realizes that it was stolen, then they can just keep using it. Okay, but what they do is every now and then they go over and they get an OCSP response for this certificate for Alice, as if they were going and visiting this website. Sorry, I think I misspoke. I talked about Alice losing it, but it's in this case, the web server like Concordia. So Concordia is the one that loses the key. As long as Concordia doesn't realize that their key has been stolen, they won't ask for it to be revoked and the adversary can continue using it. At the moment they realize that it's been stolen, they report it as revoked, and the CA decides to update the status. Okay. Now, when you ask about that certificate, you'll get, no, it's not a valid certificate. All right. But what the adversary can do is they can say, is it valid? Is it valid? Is it valid before it's revoked? Okay. And they'll get yes, 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 yes back. And they can record those yeses. Okay. Then what happens is it's revoked. Now the server's saying no. Okay. But they still have some of those old yeses that they got from the server. All right. So when Alice submits, is this still valid? And the responder says no, what they do is they substitute in one of the old yeses and they send it off to Alice. Okay. Now these responses have a time window. Okay. So they're not going to be like if you ask about a certificate and you get something that says yes, it's valid. That's only going to be valid for, I'm not actually sure what the time shelf life of that is, but it might be an hour or two. But the point is that you can extend the time that you have in order to conduct these attacks by just replaying these old ones. Okay. Now these responses are digitally signed. Okay, so they're digitally signed by GlobalSign. So you can't flip the no to a yes, otherwise you'll break the signature. But it turns out one thing you can do is you can flip it from a no to a try again. Okay, now try again is kind of weird because if you're able to send a try again message, you should be able to send a yes or no message, right? You're getting a packet and it's coming back. But in the protocol, they do allow for try again fields. And it turns out that this is in like sort of the header of the packet that's not signed. So some of the content of the packet is signed, some of it's not, the headers are not, and this is in the header. And so what the adversary can do is, even though the no is signed, they can turn the no into a try again, and then they don't have to sign it because this field isn't signed. Okay, so it's just like a kind of quirk in the protocol. But anyways, that's something else that the adversary can do. Okay, now another thing you might notice about this URL, if you look at it closely, sort of curiosity, is that this is served over HTTP. Okay, so why is it not served over HTTPS? Right? If it were served over HTTPS, then we wouldn't have to worry about someone in the middle changing the response or anything like that. Okay? And so the answer to that question is, let's imagine for a second that it was served over HTTPS. What would happen? Okay? So picture this. So you go to Concordia and you say, give me your certificate. Concordia says, here's my certificate. And you say, okay, before I believe the certificate, I need to check whether it's revoked or not. So you look up where you're supposed to go to figure out whether it's revoked or not. And let's say this says HTTPS globalsign.com. So then you go over to globalsign.com and you say, hi, I want to speak HTTPS with you. And you do this before you ever ask it, like, is the certificate revoked or not? The first thing you have to do is you have to establish that connection, right? So you say, I want to speak HTTPS. It says, great, I speak HTTPS. Here's my certificate. Okay. And you say, okay, your certificate looks valid, but I need to check whether or not it's revoked. So then you go into that certificate, you find its responder, right? And you go to that responder and say, hi, I want to talk HTTPS with you. And they say, fine, we speak HTTPS. Here's my certificate. And you say, well, wait a minute. I can't validate that certificate until I check if it's revoked or not. So then you go and you look in that certificate, you find another HTTPS address, right? And it just keeps going. It becomes a circular dependency. You can never get out of that loop because you can never create an HTTPS connection. You can never finalize it without checking whether it's revoked. And every time you do the revocation check, you're sent to another HTTPS connection that you can't finish until you check whether it's revoked. All right. So I don't know if you followed all that, but there's this circular dependency. And so that's why it's served over HTTP rather than HTTPS. And that's why the adversary can modify anything that's unsigned. Okay, so the way that you sort of get around it is you do a signature. So it's almost like sending over HTTPS. Doesn't have privacy or confidentiality, but it has integrity. But the integrity is coming from the fact that it was signed, not from the protocol itself. But if there's any like fields or headers or things like that that are not signed, you can change them because it's being served over HTTP. Now, there's an alternative to OCSP, which is certificate revocation lists, or CRLs. Here, the idea is that all CAs will just make a list of every certificate that they've revoked. Okay? And what you will do as a browser, or what your browser will do, is it will periodically go over to these CAs and it will say, okay, give me your updated CRL. And then you keep it. And then every time you get a certificate, you check against the copy of the CRL that you were given by the CA. And if the certificate's not on the list, then that's fine. Okay. Now, the problem with CRLs are, first off, there's hundreds of CAs. And remember, we don't even know of all the CAs because there's these intermediary certificates that you don't really see. So you don't see the CAs that are associated with those. Okay. So you can't really go around to all the CAs unless if you know who all the CAs are. CRLs are pretty big. So they're a couple of megabytes. They can be. So it depends. It depends on how big the CA is and how many things they've revoked. Okay. But getting things that are a couple megabytes, that's something you feel. It's not something that just, happens in the background and you don't even notice it. Okay. Especially on, like, say, a mobile phone or something like that. And you have to ask yourself, how often am I refreshing this, right? Or, maybe this was revoked yesterday. Do I want to know that or not? So then I'm refreshing it every day or every hour, so how often am I refreshing it? And so, yeah. Okay, so what some browsers do, like Chrome, is they just do this automatically for you. Okay, so let me phrase it slightly different. What Google, the company, does is it goes around to all these CAs. All right, it checks whether there's a new CRL, and then what it does is it packages it up in a much compressed format. And it sends it out to all the Chrome browsers in the world. And it does this at some level of frequency. I'm not sure what frequency it does this at. I think it's probably on the order of days, but I should check that detail. So the thing that you get is called CRL set. And it's basically a slightly, or not slightly, it's quite a bit more efficient than downloading the raw lists themselves. Okay. And this just happens. You don't have to auto update your Chrome or anything like that. It's just like some data that's sent between Google and Chrome. The problem with this is that it's very incomplete, or at least historically it was. So it was really there for emergency cases. Like there's really high profile breaches. We want to make a list of those in the browser. I don't think Google ever intended for it to fully solve the revocation problem. There was some studies, but these are pretty old now, over 10 years old, that indicated that something the majority, say 3/4 of CAs are not in CRL set. So it covers a quarter or less of all the CAs in the world. Now, maybe this has changed since then. I did try to look to see whether this is sort of the coverage is better today. I didn't see anyone who had really studied it. I saw some follow-up papers, but they were also in 2015 and 2016, and they were basically saying the same thing, that the CRL set wasn't intended ever to be 100%, and it still isn't 100% as of that time. So as far as I know, CRL set, it's an interesting proposal, but it doesn't necessarily seek out to completely solve this revocation. The other thing is that this is a Chrome thing. So this is something Google does with Chrome. If you're using other browsers, you're not going to have this, probably. It depends if the browser does it, but I'm pretty sure that, like, for example, I use Safari, and I don't think Apple does this. Now, there's a third option that's actually a brilliant solution. Okay, it's the perfect solution to this problem. The thing is, like, go back to the example of you're the CA for Google. Every time someone goes to Google, the very first time anyways, they're going to hit your server and ask about the certificate. Okay, so 10,000 people go to Google in the next second. You get 10,000 requests at your server. What could happen instead is Google could come to you and say, I mean, I know the answer to this already, but can you just confirm for me that this certificate is not revoked, and will you sign that for me? And so what your CA server can do is it can sign it once, give that message to Google. Then when those 10,000 people come and connect to Google, what Google will do is they'll send them two pieces of information. They'll send them the certificate, and they'll also send the fact that your CA server recently signed off on the fact that this is still like an unrevoked certificate, still a valid certificate. And what you'll do is you'll trust that for the next 3 hours. And then in another 3 hours, they have to go back to your server and get another one. So they're constantly, so the signed responses are kind of like certificates. Okay, so you have a certificate, but a certificate has a shelf life of 2 years. And then you have this like certificate kind of thing, but it has a shelf life of a couple hours. And so what they're doing is they're refreshing this every couple hours, but still giving it to Google once every 3 hours is a lot better than giving that same response to 10,000 people a second or 1 million people a second or whatever kind of traffic that you get. Okay, so this is great. The only problem with it is that because you're sort of changing the TLS protocol, so you're now sending an extra information. You have this extra thing, this OCSP signed response, and you're sending that down with the certificate. And what some backbone internet routers would do is sometimes they try and look inside the packets and they try and parse things out to try and figure out things about the packet ostensibly to route it better, but I'm not sure all the reasons they do it. But what they would do is they would hit this field. It was unexpected. They weren't expecting to see anything there. And then they would break, like they would drop the packet or it would cause problems for the machine. I'm not sure exactly what the issue was. But anyways, this happened enough that it wasn't deemed reliable to do this OCSP stapling because there was no guarantee that there wouldn't be a middle box somewhere. Also, I represented it as like sort of the backbone routers. Now that I recall the details, I think it might have actually been the exact opposite. It might have been more like your home routers, you know, your sort of commodity home routers and things like that were breaking. I forget where it was where these breakages occurred. But anyways, you know, the companies that experimented with this included Google, and they just concluded that it wasn't reliable enough. Too many packets got dropped, and so they stopped experimenting with that. Okay. Now, maybe in future years, as we update standards and things like that, maybe this can take a place in those standards, and we can get basically like universal acceptance of this standard, and then it won't be a problem anymore. And this will actually make the world better in terms of revocation. But as we stand today, we basically have option 1 and option 2. Neither of them are great. And so revocation effectively is not a solved problem. So you can't really rely on the revocation that's sitting there today in HTTPS. All right, here's another option. What if you just don't use a certificate at all? Okay, so this was the experience that I would see a lot on the internet maybe 10 years ago, 20 years ago kind of thing, definitely 20 years ago. Things have changed, and I want to talk to you a bit about why they changed. But this is what would happen. Websites would say, HTTPS is expensive, so we don't want to do it all the time. But we also understand that when you put a username and password in, that password is sensitive information, and so we should be using HTTPS at least to connect or sort of collect that password. Okay? So normally what would happen is you would go to a website and the website would not be over HTTPS. It would just be over HTTP. And then there would be like a sign-in button, and sometimes the sign-in button would have, like, say, a username and a password right on that page itself. Okay, so you could type your password into a page, but the page that you downloaded did not come down over HTTP. It came down over HTTPS. Okay, then what would happen is you would click the sign-in button, and the page would be coded so that any information put into that field and then submitted would actually go over HTTPS. So the website did the right thing. So effectively, you'd be on HTTP, you put your password in, you would press submit or log in, and it would transfer you over to HTTPS. The password would go across the wire in HTTPS. It would log you in, authenticate you, and do all the checks. And then what it would do is it would redirect you back to HTTP. So now that you're logged in, you now go back to HTTP. So HTTPS was just for that one window of time for collecting the password. Okay. Now there's a couple problems with this. The big problem with this is, how do you know that it's about to go over HTTPS, right? How do I know if I click that button it actually is going to go over HTTPS? And the answer is you don't. Okay. There's no indicator in the browser about whether it will or not. The best that you can do is like go look at the HTML for the document itself and try and figure out whether that submit button, is it actually going over HTTPS or is it not going over HTTPS when you submit that button? Okay. Some people thought about writing like little browser extensions and things that would try and give you an indicator, but it never took off. So you really didn't know. Now the opposite, let's say it didn't go over HTTPS, you would get a warning from the browser. We actually just saw it like a couple minutes ago, maybe a couple hours ago, but we saw that what it looks like, it gives that warning of like, you're about to submit data not over a secure channel. Are you sure you want to proceed? Okay, but generally you don't know what's going to happen. Okay, so this leads to a very simple attack. The attack is that the user basically goes over HTTP, not over HTTPS. Okay, you get the website back. The website has the button programmed up correctly, so it will go over to HTTPS. And what the adversary does in the middle is they try and re-engineer that button so it won't go over HTTPS. So they try and downgrade that button so that it just goes over HTTP. All right. Now you might think, okay, that's a pretty sophisticated adversary. They have to know how this website is laid out. They have to know what these buttons look like. They have to know where to find it. They have to, go there and actually change that button, right? And so that's a lot of work, and that's probably not like a really great strategy. But it turns out it's a lot simpler. So this attack is called SSL strip. And what you can do is you can basically, when you take any HTML file, okay, the reference to the button, the URL that button's hooked up to, has to start with HTTPS. So what you can do is you can just go through the file and you can remove every reference to HTTPS, and you can replace it with a reference to HTTP. Okay, so you don't know what you're doing. This adversary is dumb. They don't know anything about buttons. They don't know anything about the page. All they do is they just go through the website, and every time they see a link to an HTTPS resource, they replace it with an HTTP resource. Okay. Then you're going to start asking for stuff over HTTP. Maybe that stuff doesn't exist. Maybe it's only available over HTTPS, but it doesn't matter because the adversary is in the middle. So if the server starts sending back error messages, the adversary will intercept them and they're not going to pass them on to Alice. Then it will just ask for it over HTTPS. It will convert it to HTTP and then send it off to Alice. So that's what it's doing in the middle. Okay, so the net effect is that once you're on HTTP, okay, you go to this website, and the first time you load it, it loads over HTTP. What an SSL strip adversary can do is they can stop you from ever crossing over to HTTPS. Basically, you'll always stay on HTTP. Okay, so how do you fix it? Now, one thing I'll notice, though, is that if you do collect usernames and passwords doing this attack, the browser will warn you. So you also have to rely on the user clicking through that warning about, are you sure you want to submit information that's not secure? Okay, but that is something that you can click through, and if the user clicks through it, then you're able to intercept all of the traffic. Okay, so the answer or the solution to this is to move the entire website to HTTPS, so that the first thing the user does is they go over HTTPS to get the website. If it's over HTTPS, the adversary can't modify the pages because HTTPS itself is protecting the message integrity of the site, and so it's not going to let the adversary do this attack. Okay, this attack is kind of weird, but I just included it because I thought it was fun. It's also something that's like sort of dated at this point, but I thought I would throw it in. So what are we looking at here? So what we're looking at is we have a browser window, and inside of it, there's what we classically called a pop-up window. And so a pop-up window would actually pop up a new entire window. Okay, this is something you don't really see on the web anymore. Actually in part because of this exact attack. Okay, now if you want to open it up in a new quote unquote window, what it will do is it will open up in a new tab. So you'll have a bunch of tabs open. And that's actually, it solves this problem. You can think about why later. Okay, but anyways, okay, so what I have is I have some website. It launched this pop-up. Pop-up is to paypal.com. You can see the URL. You can't maybe because it's really pixelated, but I'll assure you that URL is correct. It is www.paypal.com. And it has all the indicators that this is an HTTPS connection. Okay, so this picture's a little old. So back when this picture was taken, the indicator that you were on HTTPS was a lock symbol. The fact that it's green means it's an extended validated certificate or an EV certificate. And you can even see that it has PayPal Inc. US here, indicating that this is a secure tunnel, not just to the domain paypal.com, but to the actual company PayPal that's registered as a business in the United States. Okay, so this looks great. Okay, and so imagine here there's a username and password and a login button, right? What happens if you put your username and your password in there and you click login? It should be secure. It's going to go over HTTPS. Nobody can read that password, right? Okay, so there's one problem with this. Okay, the problem with this picture is that this pop-up window is not actually a window at all. What this pop-up window is it's an image inside of the website that you're on. Okay, so you're on this website. It's adversarially controlled. And what the adversary does is they make a picture that looks like a window. It looks like a browser window, but it's just a picture that's on this website. So it's not its own window. It's just a picture. Okay. And when I say picture, you think of a static picture. It's more of, let's call it a rendering. So they rendered this this thing to look like a pop-up window. And you can render it in such a way that, when you type your username and password here, it will actually type, right? Like these are text boxes and you can type whatever you want in it. You can even have it so if the user clicked on the window bar here, they could kind of drag it around, okay, and it would sort of drag around. But if you ever tried to drag it past the user interface of the browser here, outside of the contents of the website, you wouldn't be able to do it because this is part of the content of this outer page. Okay, so by the way, we call that the Chrome of the browser. So and that's where Chrome gets its name for Google Chrome. But the Chrome of the browser is all the user interface stuff. So like the bar at the top and the scroll bars and the footer bar here, we call that the Chrome. So you have the Chrome and then you have the page content, and this pop-up window is completely contained within the page content. So you can't actually really be sure that it is an actual window. It's not just something on the website itself that looks like a window. Okay. If it's something that looks like it, then then it's something that this person wrote the HTML of, the adversary of the outer page. And so they can program this login button to send your password anywhere. So yeah. Okay. So what we do instead is we tend to open things up in new tabs instead of allowing pop-ups. And you still see like abuse along these lines. So what you do is you see like alerts and things that pop up. This isn't uncommon. And it turns out that actually if you code up a website, you're allowed to pop up alerts and you can control the text itself. Okay. Now what you can't control is you can't control the buttons here. Okay. So you can put some custom text here, but you can just have an alert that can be dismissed with okay, or you can have an alert that says stay on page or leave page. Okay. And so when people use this for fraudulent purposes, what they do is they put the fraud into the message itself. So here it's sort of like, like basically what I'm trying to say is whether you click this or you click any of these buttons, you're never going to get in trouble, right? It's just like the adversary pops up a message, they control the text, but once you dismiss it, the message is gone. It doesn't do any damage to your computer. It doesn't matter if you leave page or stay on page. There's no harm in allowing people to customize these messages. So that's why browsers allow it. So what they do is they put it into the message itself. So you'll see like, oh, you have to call this number or you have to go to this URL. It's not like click here and we'll take you directly to the URL. You would have to like read the message and copy and paste it out. So this as a vehicle for fraud, it doesn't work so well, but it is still, examples of pop-ups being abused. Okay, so we finally have reached the end of our attack tree. And so most recently we were considering this sort of thing, this node of the tree, the subtree, where we're going to try and get the tunnel pointed at us. Okay. And there was a bunch of ways to get a valid certificate. I've collapsed that part of the tree. Okay. And more recently, we talked about, could you just use a certificate even though it's not valid? So it's going to throw an error, but maybe users will click through the error. Maybe you can make it look valid because there's some sort of implementation flaw. So even though it isn't passing all the validation methods, then it's not throwing an error because there's a mistake in the implementation. There's a cryptographic attack based on hash collisions that we didn't talk about, so don't worry about that, but it's in the tree just for completeness. You could use a revoked certificate, and then you could try to disrupt the revocation check. Or you could just not use a certificate at all. Okay, so you could do the SSL stripping attack. You could do that picture-in-picture attack. Another thing I didn't mention, but you can always put locks anywhere you want on your page. So you can have lots of locks, and you can have a password field and put a lock beside it. And sometimes when users see that, they think, oh, this is secure because there's locks everywhere. Okay, but those locks don't mean anything, right? It doesn't mean that the page is secure. You have to rely on what the browser's telling you, not anything that's in the content of the page or in the favicon. So the favicon is the it's sort of hard to explain. Let me just show it to you. Let me try one other website. I'll try my personal website. You can see on my website I have this like orange slice, and so that's the favicon. Okay, and so what I could do is I could make that a lock. In the old UIL for HTTPS, the lock is how you knew that you were on HTTPS. Now it's based on whether or not secure appears or not, so it's not so useful. But anyways, that's what a favicon is. You could put a lock there, and maybe people think because there's a lock here and they're seeing it that it's a secure website, even though it's not. Okay, so this is what the attack tree looks like in its entirety. You can see it's a little big to read on the screen if we put it all together, but you can grab a copy if you're a Concordia student at Moodle. If you're watching this online, it's on my website, and you can spend some time going through it. But yeah, okay. So why did we do this exercise? We spent a long time, just to build one attack tree. But I wanted to give you a thorough example. First off, I think the issues are really interesting. Secondly, you can see that an attack tree, even though it's a high-level methodology, you can use an attack tree on anything. You can use it on hardware. You can use it on a policy. You can, anything that you could attack, you could do an attack tree for. But you can still go into a lot of detail. Okay. Now the details maybe not in the tree exactly because there's just a few words in each node. The details in the story behind each node, which normally if you were presenting this to a client or you're writing in a research paper or something like that, you would have some text for every node that explains what every node means. Okay. But anyways, the other thing is notice that if you didn't know anything about HTTPS, you wouldn't come up with this tree. So even though it's a high-level methodology, it's a way to get started, it doesn't let you find attacks in things unless if you know a lot about the underlying protocol. So we had to learn a lot about HTTPS to even understand all of these attacks. Okay. But the attacks themselves, you have a very wide breadth of attacks. So these aren't all technical attacks. Some of them are. Some of them have to do with cryptography. But other ones are like, hey, go over, use your government and go over to a CA and legally compel something, or do social engineering and try and trick someone to thinking that you still work at Microsoft, even though you don't work at Microsoft anymore. There's stuff that you saw fail open and fail close. So anyways, there's a whole breadth of attacks. And what I like about an attack tree is they can all sort of hang out in one deliverable. You don't have different methodologies because the nature of the attacks are very different. What you're doing is you're sort of letting them all sort of, they're all valid ways, and the adversary is going to choose the easiest attack. And if that involves going through a human instead of going through a server, then they'll go through a human instead. Okay. The structure can help you out a bit. So it's organized. An example of this, actually, if we just go back here, you can see like I have obtain a valid certificate, an invalid certificate, use a revoked certificate, use no certificate. So that structure sort of helps you. You sort of say, what are the other kinds of certificates? Like say I didn't have no certificate here. I'd be like, okay, I could use a valid, an invalid, a revoked, so one that was valid but is now invalid. Is there any other kind? Well, what about no certificate? And so maybe I wouldn't think of putting this node in until I see these three nodes, and then it makes me think, okay, yeah, that's another way of doing this kind of thing. So that structure, I think, also can help you like try and think about other paths that are possible. Okay, and then I mentioned this before, but attack tree sort of tells you a story. So if you were to start at the root node and kind of go along one of these paths, it would tell you the full story of the attack, and you would be able to understand it kind of from start to finish. Okay, so attack trees are great. Okay, so that was all I wanted to say. And so it was a lot to say, but we're now finally through. And so I'll see you in the next lecture.